Teaching for mastery of maths requires us to have high expectations. Now, many teachers will say that they've got high expectations, but this, perhaps more so in the maths classroom, hasn't always been the case. Perhaps if we look back to 5 to 10 years ago, common practice, certainly in primary schools, would have been teachers differentiating work perhaps 3, 4, 5 different ways based on perceived ability of children. What this actually meant was certain groups of children were given easier or more challenging work. Teaching for mastery tries to apply a set amount of principles so that all learners have the opportunity to achieve, to be successful, and to really master the fundamental of mathematics. So what might mastery look like and how might we do it? There's really 5 principles which we can draw upon when teaching for mastery. Lessons should include all 5, and they should not act as a bridge, rather they should work in tandem with each other. The first one is this idea of coherence. Lesson to lesson, having small steps to success for children to understand, grapple and engage with a concept is important. From a medium-term point of view, knowing where that concept goes within the year group and perhaps even the year group before is important for children. Having a coherent journey through all of the learning throughout the year is just as important as well. So coherent lesson designs informed by coherent planning and assessment are really important when teaching for mastery. Alongside a coherent lesson and coherent planning and assessment, we need some representation and structures when we're teaching for mastery. Now, the representations such as bar models or part-whole models allow teachers and children to explore the structure of mathematics. So, for example, children in year 3 might be learning to count up to 100 in different ways, and knowing that 100 can be made with 10 tens, or can be made with 4 25s, or can be made with 5 20s is really fundamental to their understanding. If we think about how that representational structure might play out in future when it comes to statistics, often the intervals on bar charts or any kind of graph are in multiples that we've just discussed when reaching 100, such as in 10s or 20s or 25s or even 50s. So sticking with representation and structure, it's important that children see the maths concepts in different ways. So we might think of this as concrete, pictorial and abstract representations. The concrete, we might use physical manipulatives that children can move and play with on their desks. These might be things like place value counters or double-sided counters, alongside the pictorial, which then runs alongside the abstract notation. So for example, if children were using double-sided counters in year 6 for a ratio lesson, the children might have the physical counters on their desk. That might link to the pictorial representation, which is shown up on the board, and then alongside that representation on the board might be the abstract representation, so that children can make links and look for the patterns between the concepts. The third principle is about thinking mathematically. Allowing children to reason and spot patterns doesn't happen by accident. We need precise and expert direct teaching of how to reason. There's 2 ways we might think of this. One is through the use of specific and technical mathematical vocabulary, so that children are using the language of maths. This can be words such as product, when 2 factors are multiplied together, rather than just the answer. This can be words such as the quotient, which is the answer to a division problem. When children hear this language, it really becomes embedded and children will start to use it. This depends on the high expectations of teachers, and when used correctly can really support the children's understanding. Now, running alongside the vocabulary, the use of sentence stems and structures which help children use specific and technical mathematical vocabulary can really help support the children with their reasoning and with their explanations. The fourth principle is variation theory. Variation we might think of in a really simplistic way as, imagine you're starting a lesson and you put some calculations up on the board and they're really quite random. Let's say it's fractions and you've got a half add a quarter, a fifth add a third, a tenth add 1/15th, and the children have got to kind of memorize the strategy to be able to calculate the answers to those calculations. If we think about variation theory, we can think of it as allowing children to work through the same kind of procedure, but children looking for patterns and connections. So for example, children might have on the board something like 1/5 add 1/5 equals. 1/5 add 2/5 equals. 1/5 add 3/5 equals. And in doing so, the variation, where we have kept something the same and changed something each time, allows children to make more generalizations and to look for the patterns and make connections between the mathematics that they're using. The fifth principle is this idea of fluency and allowing children to understand why a calculation works and how a calculation works so that it becomes automatic. Fluency really ought to be the ultimate aim of teaching for mastery. We want children to be quick, but we also want children to not only be quick, but to understand why that process or why that concept works. I think teaching for mastery can be a really powerful approach in primary schools and in secondary schools, so that children leave their education with a really deep fundamental understanding of mathematical concepts.